Hi Mom, welcome back to Learning Physics with me. Today we're going to be learning about springs. You may be thinking, why springs? You can maybe only think of a few things that actually involve springs in the world that you live in right now. Perhaps the shocks on your car or a mechanical pencil has a spring in it. What's the importance of springs? A lot of the things in the universe today act like springs. For example, the tides of the ocean ebb and flow like a spring. They oscillate from a maximum point down to a minimum point. And right there in the middle is what's called an equilibrium. The water is always trying to find that equilibrium. But due to some forces, the water is always oscillating. We can model this like a spring. So without finding all those forces that are acting on that water, making it rise and fall every 12 hours, we can find what's called the spring stiffness. And it's exactly what it sounds like. It describes the stiffness of the spring. We're going to use an actual spring to help you visualize what's happening. I've written down two key formulas to find the spring stiffness. It's represented here as K. The spring stiffness is found by the change in force divided by the change in length. Hi, Sophie. Now to find force, we'll just use the gravitational force, which is mass times gravity. To find the change in L, we have a spring that has a load of weight. We measure it after we add more weight to it, and this distance here is that change in L. Now we measured L, and it came out to be 9 centimeters, which is 0.09 meters. And we took the mass that we added, which was 0.1 kilograms, multiplied it by the gravitational constant, comes out to be 0.98. Don't worry about the units so much. As long as we change everything to kilograms and meters, everything will work out just fine. Now we can plug these numbers into this formula. We get force divided by the change in L, and we get our spring stiffness, which is 10.89. It's very important that we find the spring stiffness because we're going to plug that into the code, the computer model, and see if everything matches up. Another important variable that we need to find is this T, which represents the time interval. The time interval I'm talking about is this time interval right here. So the peak on this position versus time graph as the spring oscillates up, and then when the spring oscillates back down, like this. This is when the spring is at its maximum point, minimum point, and then back to its maximum point. We want to know the time that it takes for it to reach this full cycle. Now with some pretty cool calculus and trigonometry, we can create this formula right here to find out that time interval. And it comes out to be 2 pi times the square root of the mass divided by that spring stiffness that we found earlier. We're going to calculate ourselves later the time interval that we should expect. And we're going to compare that with the numbers that we see on the actual video. And we'll compare that even with the computer code. Now, I've thrown a lot of words at you. Let's actually see it.
Finally, we have the real-life experiment. Watch as the weight oscillates up and down. You can see what kind of graph it creates to the right. This is just like the graph that we drew on the whiteboard. The graph is keeping time as the weight reaches its maximum point and back down to its minimum point. We can take these times and find that time interval, and we'll see if that time interval matches what we can actually calculate.
So in the video, one cycle of the spring was 0.8 seconds. Now what we calculated using this formula, if I plugged in all the numbers, it actually comes out to be 0.74 seconds. Now let's see what the computer model comes up with.
Now here we have the code. The top portion is only for the graphs, just the visuals of the graphs, and has the X and Y axis. The second portion are the constants like mass of the weight, the gravity, and that K, that spring stiffness that we found. And then also, we're always interested in kinetic energy, potential energy, and total energy. Again, this week we are very concerned about the while loop. This week we have weight added, spring force, and force is a little bit different. For weight, mass is negative because the mass is being pulled downwards. We defined spring force as K, and it's represented here as negative K times the new block position. Again, it's negative because the force is being acted downwards towards the Earth, and it's being multiplied by the block position to update the block position. We talked about force earlier, and there it is written in code. Velocity, which is being updated by the force divided by mass, which remember that is acceleration. And finally, the block position is being updated by the velocity times that delta t, that step of time. Now let's take a look at the various graphs. This top graph is the most important one. It's that y position versus time. And here's where we're going to find out how long one cycle took. So I'm going to try and find the peak of this point right here. And it seems about 7.742. So now we can compare that with what we calculated and what we saw in the video. Now we have some other graphs here, which is velocity versus time. We're always concerned with energy versus time. And this one at the very bottom here is really cool. It's the velocity versus position. This graph is called a phase space plot. This is really cool, and it shows the cyclic nature of springs. So we got some results. The cycle that we calculated for the spring to reach that maximum point was 0.74 seconds. And when we typed it into the code with all the other variables like weight, mass, drag, not drag, but that spring constant, it also calculated 0.74 seconds. So very confident in the math and very confident in the code. We took a look at the real world experiment, and the cycle was 0.8 seconds. So it's very close, and I'm very, very pleased with that result. Remember, we did this with a real spring, but this will work with anything in nature that acts like a spring. It may not exactly look like a spring, but anything that is cyclic in nature, we can find a spring constant, and we can pretty much predict what the maximum, the minimum, and what that equilibrium is. So I hope you learned something, and thank you for watching.